spin a marble inside a smooth funnel and it circles the wall without ever sliding down. Set a coin near the edge of a record player and it rides along until, spun fast enough, it suddenly flies off. Two everyday scenes, one idea. The surface pushes back, and the push both fights gravity and bends the path into a circle. Both problems are circular motion on a surface, and both yield to the same two-step method. First, circular motion at constant speed demands a net inward force, the centripetal force equal to mass times speed squared over the radius, or equivalently mass times radius times angular speed squared. Second, the object doesn't fall, so the vertical forces must cancel. So we write Newton's second law twice, once along the radial direction pointing toward the center, and once along the vertical. The radial equation supplies the centripetal force. The vertical equation enforces balance against gravity. Solve them together, and the geometry falls out. Our first object slides without friction on the inside of a cone. The cone stands with its axis vertical and its point at the bottom. The apex half angle, the angle between the axis and the wall, is theta. The object circles at a constant speed, v0, at some radius r from the axis, and we want that radius and the time for one full orbit. Two forces act. Gravity, mg, pulls straight down. The wall pushes with a normal force, n perpendicular to the surface, aimed inward and upward toward the axis. There's no friction, so those are the only two. Now resolve the normal force. Because the wall is tilted at the half angle theta, n splits into a horizontal part and a vertical part. The horizontal part, n cosine theta, points inward toward the center of the circle. The vertical part, n sine theta, points up. Write Newton's second law in the radial direction, taking inward as negative. The only radial force is minus n cosine theta, and it equals mass times the radial acceleration minus mv0 squared over r. The minus signs cancel, leaving n cosine theta equals mv0 squared over r. This is the centripetal equation. In the vertical direction, the object never rises or falls, so the forces balance. N sine theta minus mg equals 0, that is n sine theta equals mg. Here's the elegant step. Divide the vertical equation by the radial one. The normal force n cancels completely and so does the mass. On the left, sine over cosine is the tangent of theta. On the right, mg divided by mv0 squared over r simplifies to rg over v0 squared. So tangent theta equals rg over v0 squared. Solve for the radius, r equals v0 squared over g times the tangent of theta. Notice what vanished, the mass. The radius doesn't depend on how heavy the object is, because the wall simply pushes harder on a heavier object, exactly in proportion. Finally, the period. At constant speed, the object covers one circumference, 2 pi r, in one orbit. So the time is 2 pi r divided by v0. Substitute our radius and one factor of v0 cancels, giving a period of 2 pi v0 tangent theta all over g. Now a coin resting on a turntable treated as a point mass. It sits right at the rim, a distance r from the center, and the table spins at a steady angular speed, omega. Friction is what keeps the coin from sliding, and the coefficient of static friction is mu. We want the fastest the table can spin before the coin slips, omega max. The coin travels in a circle at constant speed, so it accelerates inward, and something must supply that inward, centripetal force. Look at the forces. The normal force m pushes up. Gravity, mg, pulls down, and the static friction acts horizontally, pointing inward toward the center. That inward friction is the only thing holding the coin on its circular path. Take the radial direction first, inward negative. The single radial force is minus the static friction, and it equals the mass times the inward acceleration, minus mr omega squared. Cancel the minus signs. The static friction equals mr omega squared. So the faster the table turns, the more friction the coin needs. Vertically, the coin stays flat on the table. It doesn't accelerate up or down, so m minus mg equals 0, which gives n equals mg. The normal force just balances the weight, but static friction cannot grow without limit. Its ceiling is mu times the normal force, mu n, and since n equals mg, that ceiling is mu mg. As the table speeds up, the required friction climbs until it hits this maximum. At that instant, the coin is on the verge of slipping, so we set the required friction equal to its maximum. Mu mg equals mr omega max squared. The mass cancels once more. Divide by mr and take the square root. Omega max equals the square root of mu g over r. Spin any faster and the friction can no longer bend the coin's path, so it slides outward and flies off the edge. Step back and see the shared thread. In both problems, we split the contact force into a piece that fights gravity and a piece that bends the path into a circle. Inside the cone, the normal force did both jobs at once. Its vertical part balanced the weight, while its horizontal part turned the object, and the radius came out independent of mass. On the turntable, the normal force balanced gravity, while static friction alone supplied the centripetal pull. And that friction's limit set a top speed, 2 directions of Newton's law, every time. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.